Welcome. Today we're going to be taking a look at how we can actually use Java to do arithmetic, aka doing math with code. So we're starting off, as always in my class, with using the runner. The runner is where I just simply start up code. So you have a public static void main. I make my controller app, assign a new controller instance, and tell it to start. So we'll go ahead and close the runner since we're done with it. We never need to touch it again. We have our controller listed right here. As you can see, I've got all my code collapsed, so we can take a look at it as we need to go through and look at it. And so I have my controller class. I have a private scanner keyboard input that I'm using so I can pause the output as we work through this and step through different parts of the code. We have our constructor, we have a start method, and we have the four methods we're actually using to test information. Basic arithmetic, the rest of PEMMDAS, overflow, and mathematical comparisons. If we take a look at the start method, the one that's called from the runner, as you can see, I have basic arithmetic, then keyboard input in the next line, which is going to wait for an enter key press to happen, then the rest of PEMMDAS, then the rest of input next line again, an overflow method call, and then the next line, and finally, mathematical comparisons, how we're ending this structure. So let's go ahead and take a look at this. As you can see right here, we have our output where we have parens are just for grouping. There's no implicit multiplication. So addition, subtraction, multiplication, but division is special. And so we have addition right here. We take a look at the code that we go along with this as well. And so parens are just for grouping, no implicit multiplication. So we have addition and we have parens grouping the solution. 234 plus 456 gives us the 690 that we see here on the screen. We have 4,353 minus 176,543, which gives us the negative 872,190 value for that subtraction thing. Multiplication works just the same as normal, again using parens to group the value. The asterisk does the actual multiplication. That's the operator with it, the two operands of 743 and 7896 surrounding that value. But division is special. We have examples right here of division using ints and division using doubles. Our first one is int-based division. So as you can see, I've got 654 divided by 2134, and that gives us a value of 0. Now, if we're actually doing math in a regular math class, anytime after, say, for example, 3rd grade, we know that's not the case. We get a decimal value. But when we're using integer division, because an int itself is just a counting number, just a whole number, we have no decimal values we can even work with at all. And so small number divided by a big number is just going to be 0. There's nothing else in there. We don't hang on to it. We don't round. We just drop all decimal values. That same equation, 654.0, simply adding the decimal value to it, forces it to be a double by default. And so the numerator is a double value, gives us a double value as a result. And so 654 divided by 2,134 as a decimal gives us the 0.306, rest of the value on that. And so we can have that double value happening by using double-based division, by making sure either the numerator or the denominator is a double, or by casting, which we'll take a look at in another time. So that's our basic arithmetic, add, subtract, multiply, divide. And so here we have the rest of PEMMDAS. The first one we have is the second M, a missing M in PEMMDAS. You learned PEMMDAS back in elementary school. However, there's another M, it's modulo. And so we have system.println a demo of modulo. So 234 percent sign 5 is not percent sign 5, it's not percent of 5, no, it's modulo 5. And that result is 4 because we divide 234 by 5. We ignore the answer, we don't care about it at all. And instead we focus on what's left over, the remainder. And that remainder is what's returned from the modulo operator. And so that's where we get 4 from that. We also have 123 mod 2 is 1. And so this is a great way, one of the better ways that we can actually use modulo is to determine whether something is even or odd. It's great for processing data structures, for manipulating certain types of files based on whether or not they're even or odd results. And so mod 2, anything will either be 0 or 1, because if it's an even number, there's no remainder. But if it's an odd number, it's a 1. So we can easily do some cool features based on that. And if we're doing powers of 10, we can do some really fun stuff with numeric manipulation. I picked 200 because it's silly. And so 34,567 mod 200 is 167. That's how much is left over. And so you always have a value on modulo from 0 up to n minus 1, because n minus 1 is the maximum power. N minus 1 is the maximum remainder you can have when you divide by something, because you can't have that whole number remainder. You simply have up to, but not including that value for a remainder for that. And that's what we have for all of our modulus-based math. The rest of PEMMDAS is just exponentiation. Now, exponentiation, we can't use a superscript notation like 2 squared like we write inside our math class, because we'd already used in plain text. Even an editor still uses plain text for that, so we don't have superscripts. We can work with that. So instead, the solution for that in Java is using math.pow. And so I have right here system.println, now let's work with exponents. We'll do math.pow, and we have double base is set to 2.0, double power is set to 5.0, and we'll test that out right here. And so we have, 2 raised to the 5th power is 32. Hey, that's right, wonderful. we can also do more complex powers. In this case, I'm going to use a fractional power, aka a square root. And so I have base is set to 4.0, power is now assigned the value of 0.5, and so base raised to the power is answer, so I have 4 raised to the 0.5th power is 2.0. The square root of 4 is 2. We've got that done. And so math.power is a very functional, very powerful tool that can do positive and negative, as well as fractional powers really well. So 1 over x squared, we can calculate that easily too. So that's the cool thing we can do using the math.power, because we can send positive or negative fractional values to that and do some cool stuff with that and have really cool fractional values attached to that. So that's where we can do the rest of PEMDAS, modulo for the second M, and exponentiation for the E in PEMDAS. We already done parens, where we just simply use it to group values all throughout this demonstration. Our next one is when we're talking about overflow, really big and or small numbers. So we'll go ahead and click that, and we'll collapse this code. We're going to take a look at some really interesting things in Java. So as you can see right here, I have int big equals integer.max value and int small equals integer.min value. I'm using the wrapper class. The wrapper class is how I can handle the extra information that we need to know about integer values, but because int is a primitive, it doesn't have methods, it doesn't have data members. So instead we have this wrapper class, a special class that can work with and store information about ints and do cool stuff with them. And so integer.max value is the biggest possible int, integer.min value is the smallest possible int. And so we can do that and use other things with that as well, which we'll take out in other videos. So a system.println big contains, and then big, I get 2 billion and change. And we add 1 to big, so I'm adding 1 to 2 billion. You'd expect 2 billion whatever plus 1, but instead, look at that, 2 billion and change plus 1 is negative 2 billion. What? Add 1 becomes smaller, and so what we're seeing right here is the idea of overflow. We're wrapping over the maximum possible value, and we switch over into the negative value. It's completely flipping the sign of the value and starting going backwards through that actual value as we go through that. The same thing happens if I subtract 1 from the smallest possible value of an int. So I have small contains negative 2 billion and change, 1 more than that, take a look at that. And then negative 2 billion and change minus 1 is now positive 2 billion. Now in regular math it doesn't work, but because in Java, because with the computer we're given this specific amount of memory, and that's the possible amount of values, we have plus or minus 2 billion and change. And so when I go to the top end or the bottom end, when I go beyond those scopes, I wrap around to the other side, that corresponding amount, and it's like, oh, I went positive 4 above the maximum possible value, then I'm gonna go from the negative smallest value and go up 3 from that. It's like, oh, I've gone past that, and I'm now 4 above that negative possible value, so I can have that in there. Or if I go below the negative value, go past that one there, it wraps around from the positive and goes down that corresponding number of spots, because I have a fixed space of values. And the reason that is because of 2's complement and how we actually store information when we work with values in Java. You can take a look at that and do some cool videos and understand that in a bit more detail by researching on your own. Now let's take a look at the double value. It's a little bit different. So in the double value, you've got max value and min value, just like we did up here with int, but we're going to see some different information. So I'll scroll down so we can see the code. So let's go ahead and take a look at the double code as well. So we have the same thing again. We have double at max value and double at min value. So we assign those values, and so just like integer capital I is for the special space for int values, double capital D is the special class we have, a wrapper class, for double-based values. And we have maximum value stored in there. And so big double contains 1.79693 times 10 to the 308th power. Now, there's only approximately 10 to the 90th or so atoms in the universe. So 10 to the 308th power is redonkulously huge. So we've got way more numbers here than we can possibly ever count. So just FYI, don't try and do this. So 10 to the 308th power. So we'll add 1 to that is the same number. Oh, so it doesn't work the exact same as int. In fact, let's double big double. So big double plus big double, or multiply it by 2, twice big double, is now infinity. Oh, so you take 10 to the 308th plus 10 to the 3/8 is infinite. Well, no, because that's still a countable number. But in Java, the way we handle that is like, oh, that's too big for counting. It's past the storage space of the double value. So once we get past the positive double space of that, we represent that with positive infinity. Let's go to small double. It's even weirder. So small double contains, and we have right here, 4.9 e to the negative 324. So times 10 to the negative 324th power. So we have negative 300, we have 324 zeros times 4.9. So that 4.9 at the very end right there, hugely, ridiculously small number, fractional value. I know, it's crazy. And so we take that small number, which is less than 0, and we subtract 1 from that. Minus 1 is negative 1. Redonkulously small number less than 0 minus 1 is negative 1. Okay, mind blown, huh? Yes, but wait, let's do it again. Let's add 1 to that. Now, ridiculously small number is less than 0, add 1 to it, now at 1. Okay, so because this number is so ridiculously small, we handle this by just simply saying, oh, this number, we can't actually even store that math on this. We're just going to simply just go to 1 or -1 when we interact with that, and then correspondingly up or down from there. So the ridiculously small number, which is even smaller than the largest possible value for double, when we add or subtract from that, we're going to go ahead and get just ridiculously weird numbers of 1 and -1. Okay. It's special, it's double. Again, we're times 10 to the negative 324th value. We're not going to be worried about actually counting information with this. For more detail on this, we want to look at how we actually store values in double and how it stores the idea of the mantissa and the exponent fractions on that. But we can take a look at that in a more advanced video. But let's go one more step with this. Small double times 2 is, 1.0 times e to the 323rd. Whoa, negative 323rd. So we went from e to the 23rd. So double is just going to go 1 down. So, if I'm talking really huge numbers, I'll fraction that down just to the negative 323rd. I'll shift over 1 decimal point. Okay, no biggie. Now let's take this one more step further. Let's divide by 0. Now, if we try divide by 0 with an int, it's going to crash the computer and cause a number format exception because we can't actually divide by 0. It's going to crash and burn. But when we divide by 0 with a double, we get, in this case, we have negative infinity. If I divide by a positive number, we're going to get positive infinity. Oh, that's cool. But wait, there's more. When I take positive infinity, divide it by negative infinity, I get nan. Nan? Well, nan is not a number. It is neither positive nor negative infinity. So infinity divided by negative infinity gets us nan. We can't actually do that. And so infinity divided by negative is that special value, aka nan. And so we'll see that in some special cases right here, and we'll see it in just a second. We'll go in more detail. And move on to our next one, mathematical comparisons. So let's compare int values. We compare int values with equals equals. That's how we compare whether or not one int is the same as another int. So first 7 equals second 5 is false. That's not true. Okay, that's great. That works out exactly how I would expect it to. We try that same thing again. We assign second to 7. Hey, 7 equals 7. That's the true. Okay, wonderful. That makes perfect sense. Math works the way we expect it to. However, when we talk about comparing doubles, we have to do something completely different. So we'll scroll down right here so we can see that, and we'll press enter as well. So when I'm comparing double values, I create third, fourth, and fifth. Double third is set to pi. Double fourth is set to 3.3, and double fifth is 1.1 plus 1.1 plus 1.1, which in regular human line, we'd treat that as 3.3, right? Yeah, I know. So let's take a look at this. So system.println, third pi times fourth, 3.3 is equal to third times fifth, 1.1 plus 1.1. That makes sense. In regular math, to be totally true. However, when I say third plus fifth, it gives us false. It's not the same. Well, let's check this again. Is fourth the same as fifth? No. But 1 plus 1.1 plus 1.1 plus 1.1 is 3.3. Well, no, it's not. Because again, when we're talking about storing a double, all we're talking about right here is we only know the information we have specified. And so I specified right here, I specified the 0.3 on this. I specified the 0.1 on these. However, beyond that, there's still an entire amount of space attached to that for the mantissa that actually stores the information for that we do not know what's inside that. And so when we're talking about comparing those values, we don't know what's inside, so we can't use an equals comparison because those values after that specified amount are not the same. Instead, if we want to compare doubles, we have to do subtraction and compare the difference between that. And so we'll use another library of math on that. So we'll use math.abs right here. And so we'll use math.abs and then subtract fourth from fifth to make sure that result and see if it's close enough. And so if I set that to be 0.00_01, that underscore is how I can group things and make it very easy to read as a human, because again, we want to make things easy for us. That's close enough and it returns true. However, I set that to be 15 digits of precision plus 0.1, so 16 digits of precision beyond what we specify, then that's not close enough. And so I have to make sure that I actually have a close enough value. So this, totally close enough. 0.0001, that's really close to that value. But 0.000000000001 is really, really close, and it's not that close because we don't have that specified, so it means we can't have that be equal, and that's why we can't use the equals operator when we're comparing double values. We have to subtract them first and then see if it's close enough to what we're working on. But wait, still there's more. Let's talk about nan. Remember that's that special of infinity minus divided by infinity? It's one of the ways we can actually calculate that. So nan equals nan? False. Nan doesn't equal itself. Nan doesn't equal anything. So if I get not a number, it's not going to be comparable to anything at all. And so I get 0 results back from this. But infinity equals infinity? That's true. Infinity equals negative infinity? No, positive and negatives aren't the same thing. But negative and negative, those are both the same. So we're good to go. And so I hope this is helpful. We learned how we could do some comparisons inside Java. We talked about how we could do mathematical comparisons. We talked about the extremes of ints and doubles when we talked about overflow. We talked about the rest of PEMMDAS, the two missing things we didn't do in a basic arithmetic, the missing M of modulo, as well as exponentiation using math.pow. And finally, we did basic arithmetic, add, subtract, multiply, divide. And remember, when we're talking about division in Java, it's special. Ints are are one thing, doubles are another. And so you have to keep that in mind. Hope this is helpful. Cheers. We'll see you and have a great time. Bye-bye.